Hello, it's Mrs. Pound, and I am back with a new chapter. We just finished chapter 1.3, and we're continuing on into chapter 1.4, where we're talking about chemical interactions. So, the first thing we need to talk about is section 141 about chemical formulas. So, our objectives today are to determine the identity and quantity of elements in a chemical formula, distinguish between molecular, structural, and empirical formulas, and calculate the mass of simple and complex molecules. So, a chemical formula is an expression that identifies the types and numbers of elements present in a compound. There are three types of chemical formulas that we're going to take a look at. The first is the molecular formula. This indicates the identity and quantity of all elements present in a molecule. So, an example is glucose, and its molecular formula is written as C6H12O6. Notice we have the element symbols, and then the quantities are listed after the element symbols as subscripts. These are smaller numbers below the symbols. So, what the 6 after the CSAT tells us is that there are 6 atoms of carbon in this molecule. The 12 after the H tells us that there are 12 atoms of hydrogen. And the 6 after the O tells us that there are 6 atoms of oxygen. Let's look at something a little more complex. This formula, Al2SO4 has parentheses in it. The parentheses tell us to multiply. They're a lot like parentheses in algebra. So here we see the aluminum is outside of the parentheses and there's a 2 after the Al. So that tells us that there are 2 atoms of aluminum. For the things inside of parentheses, we have to multiply by 3. Now the S does not have anything after it, so it's assumed to have a 1. Just like algebra, we don't write 1x, we just write x in front of it. And so the sulfur, it's 1 times 3, which is outside of the parentheses, so there are 3 atoms of sulfur in this molecule. And for oxygen, there's a 4 after the O and a 3 outside of the parentheses, so it's 4 times 3 equals 12 atoms of oxygen. Another type of formula that we commonly see is a structural formula, and this provides a visual picture of a molecule. These actually give us the most information. So here is a structural formula for water. There are 2 hydrogens, There are 2 hydrogens and 1 oxygen. So H2O. So it not only tells us the quantity, and the type of atoms present, it also shows us how they are arranged. So we get a lot of information here. And here is what glucose looks like. This long chain of carbons in the middle with oxygens and hydrogens attached to it in a certain arrangement. If they were arranged differently, it would be a different molecule. There are also empirical formulas. These show the simplest whole number ratio of atoms. So an example is, let's use glucose again. So we start out with glucose, but we notice that all of these numbers are divisible by 6. So we're going to divide each one by 6. Okay, that's what I've represented here. And when we do that, we end up with a 1 behind the carbon, which we don't write, 2 behind the hydrogen, and a 1 behind the oxygen that we don't write. So the empirical formula for glucose is CH2O. Now there are a lot of things that have this empirical formula, so this isn't as helpful, but empirical basically means experimental. So when we do experiments, we could come up with this formula perhaps for the ratios between these different elements. One thing you can do if you know a molecular formula is you can determine the molecular mass. Molecular mass is calculated by finding the sum of the atomic masses. So, an example would be determine the molecular mass of butane. We see that butane has a 4 after the carbon, so it has 4 carbon atoms. Now let me switch over to the periodic table. We see over here on the periodic table that its atomic mass is 12.011. So, what we do is we multiply 4, because there are 4 atoms, times 12.01 grams, 11 grams, and we get 48.044 grams. Now we look at the hydrogen, the H, and we see that there are 10 atoms of hydrogen. So we write that down, and then we take a look at our periodic table here, and we see that the atomic mass is 1.008. So we multiply 10 times 1.008 grams and get 10.08 grams. What we do then is we add those two numbers together and get 58.124 grams. That is the molecular mass of butane, the mass of the whole molecule. Okay, so if we can calculate the molecular mass, we can also calculate the percentage of mass. So a question might ask, what percentage of mass of butane is carbon? So we have to remember this formula, and I will give this to you. The percentage of mass equals the part over the whole times 100%. What I mean by this is the percent mass is the mass of the carbon, because that's the part of a molecule, over the mass of butane, the whole molecule, times 100%. Now we just use our numbers from our molecular mass that we found in the previous problem. We say the percent mass is 48.044 grams, which was the total mass of all the carbons in butane, over 48.124 grams, which was the mass of the butane, times 100%. When we put that into our calculators, we get 82.658%. So let's try another problem. Let's find the percentage of mass of butane. What percentage of mass of butane is hydrogen? So again, we start with percent mass equals the part of the whole times 100. Or in other words, the mass of the hydrogen over the mass of the butane. We plug in the mass of the hydrogen atoms, which is 10.08 grams, the 10 hydrogen atoms, over the total mass of the butane, which is 58.124 grams, and we get 17.342%. Now, here's a check. We better make sure that these numbers both add up to about 100 when rounded off, and they in fact do, but go ahead and check that. If they don't, you've done something wrong, because we looked at both parts, the carbon and the hydrogen, and so they should add up to 100. So our objectives today were to determine the identity and quantity of elements in a chemical formula, distinguish between molecular, structural, and empirical formulas, and to calculate the mass of simple and complex molecules. So don't forget your 5 questions, and I know there was a lot here. We're going to be working with this in class.